My name is Konrad. I'm a professor of mechanical engineering at Arizona State University. And today I'll talk about the project that I've done with a few of my master's and undergraduate students over the past year or so. And it focuses on the impact of body shape on radiation and convection. So, introduction. It is hot, and I'm just going to show you what Giselle, and let's see more of those. Ari in the back have just lived through. Well, this is what Phoenix used to look like in the summer. It's the desert. It's always been hot. Okay, for you, we talk in terms of Fahrenheit, but in parentheses you have Celsius. Main point. The high was maybe 106, so about 40ish. The low was about 80 something, but it used to cool down below 80, right? So it used to go down, and nights were cooler, which we just heard what is good. Unfortunately, this is what happened this summer. So everything went up, right? We beat the record for the entire month. The highs were about 110 degrees, which is 43.3 degrees Celsius. It never cooled off. Every morning, it was about 31, 32 Celsius, or how the reactor actually beat the record, which showed up or not. Yeah, we beat the record for the low. It was 97 degrees Fahrenheit. Why does this happen? Climate change, yeah, partially. Well, like about 4 million more people moved into Phoenix in that 50 years. And we also paved over the entire valley, right? So this is why this is happening. And then you start thinking, okay, so we look at how is the human body heated or cooled, and really radiation, convection, right? The air is so hot that you're not cooling off with it, it's heating. That does the heating. Then cooling, right? Despite being hot, the air goes over you, it's dry, it evaporates you, and that's your primary heat sink. You also emit a little bit of radiation. Okay, great. Now, the question is, how does that vary with the human body shape, right? A lot of the models we heard about so far, or the inputs you've done, they were really developed for an average person. So we found this database. I don't know if anyone's familiar with it. It's from Penn State University, where you can kind of type in the body mass index and the height, and it spits out mannequins that are actually measured on people that try to be near that percentile for it. Then you can get a three-dimensional file from that, which spits out one of the world's worst meshes to do any simulations with. So my students and I spent 6 months fixing these meshes so we can actually have something useful. So just to give you kind of a perspective, right? In the past, if you look at the measurement of the heat transfer coefficient of projected area factors, and there's a disclaimer, we can't do that. Predominantly, they've been measured for the average Western male or female. So this is, we added the rest of US population to that. So we have about 60 computational mannequins that represent the diversity in terms of gender, body mass index, and height. I know body mass index is not the best measure, right? Because you can have a guy who's very muscular, spends his life in the gym, and he'll have a body mass index that tells him that he's unhealthy. But it's a measure that we can have. So from here, right, and this is again 1 to 99 percentile in the adult population in the United States. From here, we first look at convection, right? So we can take our different mannequins, we build a computational wind tunnel, and we validate it for available models against similar methodology, and then we fix the environment and run our mannequins through that. For radiation, we looked at projected radiation area factors, and if you're not familiar with it, it's essentially you take the total area of the surface of the body and multiply times the view factor between the mannequin and the environment. And that gives you the effective radiation area, which is essentially the fraction of your total body that interacts with the environment from a radiation perspective. Then we look at the directional radiation, right? So let's say the sun, where you're exposed directly from here, you cast a shadow behind that. That's the projected area. And it's more or less a fraction of your surface area. So the projected area factors is the ratio of this shadow to this effective area. So I'll be talking about exposure in terms of that. All right, so first let's look at convection. So you can do a plot, right? You can do female and male, and you can take the average and then the two extremes, very skinny and the opposite. And you can plot it as a function of height, right? Does the heat transfer coefficient change? And height has no impact whatsoever. Then you look at increase in body mass index, and you see almost a linear decrease. However, when you look at the kind of absolute value of the actual heat transfer coefficient and how much change you see, it's only about 15% between the smallest and the largest person. And if you've ever done measurements in this area, this is really within the experimental uncertainty of some of these measurements. The error bars are relatively large. So BMI has some impact, but it's not very high. You can then try to break it down into a little bit more detailed picture. You can do flux maps. These are not that informative, so you can then start looking at regions of the body. And then you see the same type of trend where essentially the heat transfer coefficient on almost every body part decreases with the body mass index. What does that mean? The diameter is getting a little bit larger. So if you look at the Reynolds number, the physics of that, it's proportionally decreasing with that. Okay, so it makes sense. However, the overall impact is not very large. All right, so now moving on to radiation, and here I really hope I have a subtitle. There has been some great work done in the past in that by Professor Park over here. The problem is he looked at overweight and obese Canadians 15 years ago. Americans have expanded substantially, and if there is one thing you can count on is Americans expanding over time in general statistics. Not good. But from what I remember about like the maximum BMI you looked at is currently an average American. Right, so I think I had BMI up to like 30-ish, and that was like your extreme, and then I look at it and I think the average American is 28 now. Not good, but since we weren't covering half of Americans, we decided to look at it. So you can do then, right, we look at this in terms of, you can think of the sun, right? So we look at the sun going up and down, and then you're rotating around. I'm trying to wake up people, right? It's late enough. I'm trying to wake myself. So you can then look at different solar angles, right? So zenith angle, and then this is azimuth, so this is the rotation. And it makes sense, right? As you're facing irradiated from here, you have less exposure than when you're radiated from here. This is what this does. And then again, we do the same exercise, right? So you have the mannequins here as a function of height, no effect. You look at the function of BMI, so here we fix the height and look at increasing BMI, almost no effect except at very, very low angles, right? So this is when sun is kind of straight down. All right, so let's dig into that a little bit. So here, this is irradiation straight from the top, and we look at just absolute BMI, or if you want to look at the percentile here, for male and female, and we see that the larger the BMI, the larger is this projected area, right? The larger shadow you cast. Now, the twist here is that the difference in here, right, is comparable to when you go from standing up like this to doing that. So it's very small. You put on a hat, you change this value by about the same effect as if you go from 1 percentile to 99 percentile. So in overall terms, I think it's not very important. All right, so conclusion. Body shape has relatively minor influence on forced convection and radiation when it's scaled by the total body surface area, right? So this is heat transfer coefficient is per area. The projected area factors were also per area. So if you're larger, you have more surface area, you're getting heated more in terms of watts, right? But when you scale it by the surface area, it doesn't matter that much, which is a kind of boring outcome for a paper, but it's relatively good in terms of providing, right, everything that we've measured so far for the last 100 years or however long we've been looking at thermal regulation does apply to most of the population in reasonable terms. We're looking at natural convection right now, but we have a thermal mannequin, so we're actually trying to validate it experimentally and then before we run it, and it's in progress right now. So, implications. One is, okay, so our models are valid. Two is, how would you make a sensor in this case to look at radiation? You could make a human-shaped doll if you want to be really accurate, but then you start running into these problems, how do you orient? So you have to make some kind of a simplification. The easiest one is to say we are rotationally symmetric along the axis from your head to your toes. I've been talking about this for a little while, so I thought, it would be kind of interesting to actually see what would it look like. So I took these mannequins, I calculated the areas, cross-sectional areas at every centimeter, and then say, okay, let me combine and translate it to equivalent radius. And this is what it looks like. I made a bunch of little Oscars. Essentially, right? So keep in mind, right, this is, under this assumption, this rotation is symmetric, you can then take and plot the rotationally average projected radiation error factor. So again, for little Oscars, not for real humans. And then you can plot it against a cylinder. And it doesn't really matter what the aspect ratio of the cylinder is. They represent, right here we have this 1 percentile to 99th and 50 percentile. They do a great job. So if you want to have a sensor that tries to measure how much radiation a person gets, make a cylinder. And this is what we've been doing over the summer. If you're interested, talk to me. We have some interesting results on that case. Thank you for your time. And
any question?
Thank you. James Morgan from the University of Sydney. Lovely presentation, very interesting. I'm also very excited to see your new acquisition in your new thermal mannequin.
Oh, yeah.
Excited to see some future research. Really nice experimental design. I just wondered if you considered using a similar modelling approach to examine the impact of these differences in body surface area on evaporative efficiency. So you then can potentially take a more holistic analysis of the effect from a heat balance perspective.
Sure. So, ongoing, we have a lot of interest in sweating because we do a lot of it. If you remember my first slide with the temperatures. In general, right, if you look at the physics, theoretically, in forced convection regime, evaporation is almost directly proportional to evaporation, right? So if you don't have much impact on the heat transfer coefficient, you also don't have much impact on the mass transfer coefficient with Lewis analogy. Now, there is a lot of other things about that where right now, my thermal mannequin and everybody in general assumes that sweat is uniformly distributed over the body, which is not true. And that is an interesting aspect. Another thing comes back to natural convection, where there's some intricacies with how the physics happens, where they're not directly proportional to the heat transfer coefficient. So great question. Probably some impacts in certain cases for sure.
Okay. Oh, one more question. Yeah, the last one.
Thank you for your interesting presentation. I was wondering, you work with mannequins and you do a lot of experiments. Do you also cross your results with the one of thermophysical approaches that real you want to see to do cross analysis? Yeah. And if yes, how do you do and what does it give as a crossing analysis?
This is a $2 million grant we just started,
yeah, okay.
And that's part of it. But it's not. It's just not. Yeah,
it's not. Next presentation. For the next.
Yeah, it's, okay. So it's ongoing. Yes,
okay.
Absolutely, you need to.
Okay.
We're just not there yet.
So we'll wait 3 years.
Hopefully.
Thank you.